Okay, so in 15.3, we talked about how we can estimate the area underneath the curve using rectangles. We figured out what the base was, we figured out what the height was of each rectangle, and we did base times height, base times height, base times height, and we added them all together. Unfortunately, though, that was just an estimate because some of our rectangles were above the curve, some of them were below the curve, and it wasn't very exact. And we discussed that the only way that we can get an exact area underneath the curve is by taking the base times the height, the area of a whole bunch of different rectangles, adding them all together. But in order to make it exact, we needed to make sure that we had an infinite number of rectangles. Well, we couldn't possibly do base times height, base times height, base times height an infinite number of times. So we discussed that finding the area underneath the curve is the same thing as finding the definite integral, finding the antiderivative of f from a to b. So that's kind of what we're going to discuss here in section 15.4. It's called the fundamental theorem of calculus, where if I ask you to integrate from a to b, what you're really just doing is finding the antiderivative, just like we did before, from a to b. So we're finding the area underneath the curve of our function little f from a to b. Okay? So let me give you kind of an example comparing the two different ideas that we've discussed, indefinite integral versus a definite integral. So looking at example number 1 with me, the first one says to find the integral of 4t cubed with respect to t. Find me the indefinite integral. What that's saying is that my 4t cubed is my derivative, and I want you to find me the antiderivative. What original function has a derivative of 4t cubed? Well, in section 15.1, we discussed all the different rules for antiderivatives. We can use our power rule. We can add 1 to the exponent and divide by that new exponent and come up with an antiderivative of t to the fourth plus c. And so what that is a whole new function that represents the original function whose derivative is the 4t cubed. So he's a whole nother function representing the antiderivative. Now, it changes a little bit as soon as I add these limits of integration. What this is saying now is I want you to find me the area underneath the curve of 4t cubed from 1 to 2. Or another interpretation is find me the original value from 1 to 2. Find me the change in my antiderivative from 1 to 2. So I can follow the process like we were doing before by finding the antiderivative using our power rule. But instead of adding that constant of integration, because I'm not actually looking for a function, now I'm looking for an actual value. I want to know what the value is of my new function from 1 to 2. So some books use like a straight line here, some books use kind of a bracket to represent that we're evaluating it. But what that means we're going to do is we're going to take this t to the fourth, this antiderivative, and we're going to evaluate its change from 1 to 2. So in order to figure out the change, we've got to plug in the upper limit, the 2. We're going to plug in our lower limit, the 1, and then we're going to subtract them to find the change. And so I end up getting a change of 15. So my integral of 4t cubed from 1 to 2 happens to be 15. That's the same thing as asking you for the area underneath the curve of 4t cubed from 1 to 2. That's the same thing as asking you for the original function values change, net change. Okay, before we keep going with our fundamental theorem of calculus, let's discuss a few properties of definite integrals. So we just discussed that a definite integral is really the same thing as finding the area underneath the curve. So if I ask you to evaluate the integral from a to a, you should end up getting 0. Let me discuss what that means. So if I say the integral, evaluate the integral of f of x from 3 to 3, what I'm really asking you to do is find me the area underneath the curve from 3 to 3. Well, if you start at 3 and you end at 3, you haven't really gone anywhere. So there really shouldn't be any area. And so that's why the area underneath the curve from a to a is 0, because you really don't have any area. The second rule says that if you have a constant, just a number, just like our rules with derivatives and antiderivatives, we can actually take that constant out to the front, integrate the rest of my function, finding the area underneath the curve, and then just go back and multiply it by whatever that constant is. Same idea with rule number 3. if we have two separate terms and they're only separated by plus or minus signs, then we can evaluate the integral, the area underneath the curve of one of them. We can do the second one, and then we can just add or subtract our two answers together. Rule number 4 says something to the effect of, if I don't know the whole entire area underneath the curve, but I know the little pieces, I can simply add those together to get the full amount. For example, if I know that the area underneath the curve from A to C, I don't know, is 10, and then the area underneath the curve from C to B, let's say, is 7, well, then I can clearly say that the area underneath the curve from A to B, the whole thing, should be 17, right? Just adding them together. And so if I know the little pieces, then I can add them together to get the big piece. Or I can use that rule backwards. Maybe I know the big piece and one of the little pieces, I could subtract it to figure out what the other little piece is. Okay? The last rule says that when I'm integrating and I have a definite integral, when I have my limits of integration, it should always be read from left to right. So those limits, the numbers at the top and the bottom of my integral sign, should always go from least to greatest. And if they don't, what I need to do is I need to flip them around. But in order to flip them around legally, I need to make sure that I make my answer negative, or the opposite of whatever my answer was. For example, if I ask you to integrate f of x from 7 to 3, normally it doesn't go in that order. It would go from 3 to 7. So I would have to flip it around, integrate it just like normal, finding the area underneath the curve from 3 to 7, but then I would need to make sure that I added a negative in front of my answer. So making sure that your limits of integration